So welcome to the next talk of the CDY Initiative. And today we're going to hear about NuSTAR results. NuSTAR is a instrument that can detect from X-ray instrument, can detect from a few kV up to 80 kV. So it has a very broad X-ray range. And the big claim to fame is that it's also a pointed instrument and it has a good angular resolution, unlike some of the earlier hard X-ray instruments. And today we have Mori, who will be the speaker, and he's from Columbia University currently, where he's a research scientist in the Columbia Astrophysics Laboratory. And as we're talking beforehand, well, he used to be a graduate student at Columbia University, and then and before he was a graduate student, I guess he was at the University of Tokyo. Is that right? Okay. And then after getting his PhD, he went to the Canadian Institute for Theoretical Astrophysics, and then he went back to Columbia, where I guess he's been ever since. And his claim to fame or expertise is working on a variety of galactic high energy sources, such as the galactic center, X-ray binaries and transients, TV gamma ray sources, pulsar, wind nebulas, supernova, remnants, everything, especially in the galactic plane. And he led the NuSTAR Galactic Survey, where he's had numerous publications on NuSTAR observations, and he's also part of the Galactic TV collaboration group in NuSTAR. And I also know him because he's one of the leaders of the HEXP probe concept that NASA's trying to launch, which will be basically a super NuSTAR. And I guess he's leading the galactic science there also. So he's in a good position to tell us about high energy X-ray observations of sources, particularly in our galaxy. And for those of you who are used to, in the audience, are used to TV energies, working at nano TV, KV energies may not seem that interesting, but I'd just like to remind you, and Kaya will probably tell you for sure, that often in galactic sources especially, the emission is polarized in X-rays and reflects the synchrotron emission from the highest energy electrons in the source. So it's actually a very good, useful probe for what's going on in extreme accelerators. So with that, I'll stop talking and let Kaya take it away.
Okay, thank you, Paolo. Nice introduction. Okay, so again, my name is Mori. I'm working at Columbia Astrophysics Laboratory. I work at C part of the CDY lecture series. So I already changed my talk titles quite selfishly from a very generic title on the website to highlights from NuSTAR observation of galactic high energy, mostly TV sources. Why? Because when Rashmi asked me to give a talk, I was wondering what to talk about because it's such a broad band of topics to talk about NuSTAR results over the last 11 years. So I looked up the CDI website and I found this picture. So it says extreme non-thermal universe and then understanding the extreme acceleration. And I see a picture of Crab Nebula, which is a very famous leptonic accelerator in our galaxy, and the galactic center. So I decided to talk about these topics in our galaxy. So just hacking the CDY website with NuSTAR images. On the left, you can see a Crab Nebula in the hard X-ray band about 35 kV. In the middle, that's the hard X-ray view of the galactic center taken by NuSTAR between 10 and 80 kV. So I'm going to talk about these topics today. So here's the outline of my talk. I will talk mostly about non-thermal diffuse X-ray sources associated with galactic TV sources. And then that means I will not talk about accreting objects like X-ray binaries or transients or extragalactic sources or thermal X-ray emission. If you're expecting these topics, I'm sorry, but I just don't have time to go over these, and I'm not an expert on the extragalactic sources. So in the first 10 minutes, I'm going to go overview the NuSTAR telescope and then its observation program over the last 11 years. And then I'm going to move on to the science part, starting from a supernova remnants. I'm not going to cover everything, but particularly Cas-A, and then pulsar nebula, and other TV sources, some selected group. And then finally, I'm going to talk about the galactic center. And in the last 5 minutes, I'll be talking about the future X-ray telescope landscape in 10 years, especially X-ray probe mission and the HEXP concept. Okay, let me start with what the X-ray telescope are doing right now. So on the bottom, you can see three pictures of Chandra, XMM, and NuSTAR. They have been doing a great job, especially for Chandra and XMM. They have been running for over 20 years. So Chandra has a very good angular resolution down to 1 arcsecond, and it operates between 0.1 and 8 keV. On the other hand, XMM Newton covers pretty much a similar energy band. It's called a soft X-ray band below 10 keV, but it has a very large effective area and field of view. On the other hand, NuSTAR covers a higher energy from 3 to 79 keV. So that's where NuSTAR is unique in the X-ray community. So these are not the only X-ray telescopes running right now. So we have SWIFT and NICER and MAXI. So these telescopes are very good for time domain astrophysics, basically catching X-ray transients. And then we also have XP, which was launched back in December 2021. So this is a specific telescope measuring the X-ray polarization, the soft X-ray band below 10 keV. And then we have ERO-Zeta, that's an all-sky survey X-ray telescope, but currently suspended. It's suspending a science operation due to the ongoing war in Ukraine. And then Japanese JAXA and NASA, they have a joint CRISM telescope coming up and to be launched this year. And then it carries a microcalorimeter, which will give you a very good high resolution energy spectroscopy in the soft X-ray band. Again, so among these X-ray telescopes, NuSTAR is unique. It covers higher energy. Okay, so this is a snapshot from NuSTAR website. If you are curious about NuSTAR project and then what it discovered, you can go to this website. This is from Caltech website. And then you can also go to NASA's NuSTAR website. So the catchphrase for NuSTAR has been bringing the high energy universe into focus, because NuSTAR is a focusing telescope operating about 10 keV. So on the right, you can see effective area comparison between different X-ray telescopes. So as you can see, Chandra, XMM, and SWIFT, they have effective area going up to around 8 or 10 keV, but NuSTAR goes beyond 10 keV, all the way up to 79 keV. So its angular resolution is around 58 arcseconds for the half power diameter and 18 arcseconds for resolving power. And then field of view is around 12, I mean, it's official, it's around 13.6 by 13.6 arc minutes. And then it has a good energy resolution, less than 1 keV throughout the energy band. And it also has a very good timing resolution below 0.1 millisecond. So you can really measure the pulsations from millisecond pulsars and pulsars. So the PI of the project is Fiona Harrison at Caltech, who was leading the NASA Decatur survey recently. And then NuSTAR's optics was built at Columbia University, and the lead was Chuck Cayley. He's a professor at Columbia physics department. And the detectors are developed at Caltech. So it's a combined Columbia, Caltech, NASA Goddard, JPL, some other institutes from Europe. It's a joint NASA's project, which started almost 15 years ago. So let me talk a little bit about what happened to NuSTAR mission over the last 11 years. So NuSTAR is a NASA's MEX mission, launched back in June 2021. So on the right, you can see a NuSTAR's anniversary poster celebrating 10th year of NuSTAR operation. So you can see NuSTAR has a very nice nickname of a black hole hunter or finder. So that's some central black hole inside AGN or the X-ray binary. Actually, NuSTAR is actually pointing away from black hole. So the inside joke is we have another black hole on the opposite side. So anyway, so in the first 2 years, we had a primary mission led by the PI institutes. So Caltech was mostly in charge of an extragalactic survey. Columbia team was mostly in charge of a galactic survey. So we kind of divided up these big tasks. So after 2 years, we started something called a legacy program. And then at that time, we started looking into galactic TV sources. And then after the third year, NuSTAR opened up its observation time, the GEO program. So anyone can write a proposal, and then win a proposal, get a new observation for your favorite observations. So now NuSTAR is in a mature stage. So compared to the first year, when we had only 2 TOs in the first year, now we have many TOs because there are so many transients being found in other wavelengths. So it's a very good instrument for doing a time domain astrophysics. And then also, NuSTAR has done a lot of joint observations with other X-ray telescopes, like NICER, Chandra, XMM. And then also we have done observations with Veritas too. So that's another thing NuSTAR is getting into. And then NuSTAR also opened up a large program, GEO proposal category. So you can propose for big chunk of an observation like above 500 keV. That's very expensive usually for a GEO program. So this is for you to go for high risk and high return science. So this is also opening up in the opened up over the last 4 or 5 GEO cycles. So let me give NuSTAR another good nickname. So I would say NuSTAR is an excellent non-thermal X-ray emission detector. So as you know, many of the X-ray sources actually do show thermal emission that's easy to produce between like 0.1 to few keV. So it's always there. When you talk about X-ray binaries and neutron stars, CVs, supernova remnants, star clusters, and then but NuSTAR can really go to higher energy, about 10 keV. So you don't have any contamination from a soft X-ray thermal emission. So that's going to open up a window, clean window to look at the non-thermal X-ray emission. So I'll give you one example. So on the right, this is NuSTAR view of Jupiter about 10 keV. So this was the first time the hard X-ray was detected from Jupiter, and it's actually the highest radiation ever detected from Jupiter, all the way up to 40 keV. On the bottom, you can see a NuSTAR spectra, very hard power spectrum, and then it was actually measured during the NASA Juno mission orbiting on the planet, taking an electron spectrum just above the atmosphere. So we input the Juno's electron data and then input them into our simulation through a GM4 and then produce a nice X-ray model spectra, which exactly match with a NuSTAR spectra. So this is like a beautiful demonstration of how NuSTAR can measure a non-thermal emission, in this case, non-thermal Bremsstrahlung emission from Jovian aura, and then applying a physically motivated model and explain the whole physics here. So I'm now going to talk about Jupiter for the rest of my talk. So another aspect of a NuSTAR, unique aspect of NuSTAR, is it explores synchrotron radiation from TeV and PeV electrons. So as you know, many energetic particle accelerators produce TeV and PeV electrons. Whether you have a primary electron sources like PWN, or if you have hadronic accelerators, you can produce a secondary electrons from proton-proton collisions, producing pionic showers, cascading into the electrons. So these electrons should have TeV to PeV electrons. So these electrons produce synchrotron radiation in the X-ray band, especially in the higher X-ray band. If you have a very energetic electrons, like 100 TeV or PeV electrons, and then it also depends on the magnetic field. So you can see an example SED model from a NIMA website. I'm pretty sure many of you use a NIMA SED models. So on the left, that's a synchrotron component bump. And on the right, you can see an inverse compton scattering bump or hadronic, sometimes hadronic component to be studied by Fermi-RAT and TeV telescope. So NuSTAR band is very sensitive to some kind of spectral rollover or cutoff at the higher energy of the synchrotron component. So we are sensitive to Emax of electrons. And then at the same time, if you're talking about higher energy electrons emitting hard X-rays, so they tend to cool faster. So you might see a fast hard X-ray variability if you have a higher B field. Okay, so let me talk about how we or many people actually explore the galactic TeV source in the X-ray band. So let's say LASSO detected a new source, HAWK detected a new source, Veritas reported something, Hess reported new TeV sources, and what do we do? So we want to follow up with X in the X-ray band. Usually, most of these galactic TeV sources are extended, and then sometimes not very localized, and then you might find multiple counterpart candidates with some offsets. So I would say go with XMM with a larger field of view, just to see what's going on, what's out there in the soft X-ray band. And especially because these sources have a power-like spectrum, so if you go to lower energy, you get more count in the soft X-ray band. And then once you find something in the XMM data, for example, this is a HJ1826-130. This is associated with the E pulsar nebula. We published a paper last year. So XMM really sees a pulsar here and some kind of compact nebula and extended diffuse emission. So NuSTAR can really follow up and say, okay, let's just focus on the pulsar part, what do you see? So about 10 kb, this is a NuSTAR image of a compact nebula just around the pulsar, but we didn't find, we didn't detect any diffuse X-ray emission, which was detected by XMM in the soft X-ray band. So this is sort of a regular procedure to do large field of view, soft X-ray observations first, and then follow up pinpoint observations with NuSTAR, just to pick up the non-thermal emission. And then you can do spectroscopy and then morphology study. So let me go to the fourth year of NuSTAR program when we started the NuSTAR legacy program. So at that time, we are looking for some kind of high risk and then long observation type observations, and then maybe even like start a new program. So we were approached by a folk team and also Veritas team through Reshmi. Reshmi has been our very good collaborator for a long time. And then we had a long discussion about, okay, maybe we can start something between X-ray and the TeV band. So we picked up 3 galactic TeV sources. The first one is a PWN called the DA495. And the second one is a TeV gamma ray binary for the HJ0632. And the last one is a Hawk source 3HWC J9088. I think it has a 3-Hawk name now in the new catalog. So we looked at these sources more like a pilot program. So we started with a NuSTAR Veritas Hawk collaboration, kind of small, and then now it's evolving into a large group of 40 members. We have Zoom meetings every month, talk about all kinds of TeV sources in our galaxy. And then we also proposed many X-ray observations. They are approved and then performed until now. And I'm going to show you some of the new results. Okay, so what we ended up with these pilot programs. So again, by studying the pulsar nebula called DA495, again, NuSTAR detected some compact X-ray nebula. We did some NCD study. So we decided, okay, maybe we can go big and then look at the other middle-aged PWN. So that our NuSTAR large program proposal was approved, and then we observed 8 middle-aged PWN, which I will talk about later. And then for the TeV gamma ray binary, HJ0632, so it has some kind of peculiar X-ray light curve shape. We just looked at the 2 of the phase intervals and then just extracted the NuSTAR and Veritas SCD data. It's in the pre-flare phase, so it's not covering the entire orbit. So yeah, why not? We should just go for other orbital periods and then do the observation. So that's what we did next. And the last one, the Hawk source, NuSTAR didn't detect anything in the field of view. There's one X-ray point source here, also detected by Chandra, but I don't think that's the X-ray counterpart of the Hawk source because it's not diffuse X-ray emission. So we kind of step back and say, okay, let's go back to basic and then do the XMM Newton survey of all these LASSO and Hawk pivotal sources. So I have my large XMM proposal accepted last year, and then we're going to be observing 4 LASSO sources this year, including J2118 observation happening this month. So that's going to be exciting. Okay, so let me talk about any questions so far. Okay. If not, let me start talking about supernova remnants. Okay, I'm going to skip all the SNR introductions, but I'm just going to go straight into the hard X-ray views of young SNRs measured by NuSTAR. So 5 young SNRs, Cassie SN987A and Tycho and Kepler, and then G is 1.9.3.3. That's the young SNR in the Galactic Center. We observed these young SNRs for a long time. For example, Cassie spent 2.4 megasecond. Why? Because the primary science goals for NuSTAR is to detect and study titanium-44 lines from young supernovae remnants. So that's going to give us a very robust and direct probe of exploring supernova explosion mechanism. So that's another topic I'm going to cover. But we successfully mapped the titanium-44 line detection from CASA, not just a two-dimensional map, but we also measure the red shift and blue shift, so we can do a three-dimensional Doppler tomography of titanium-44 lines. And then we published a paper in Nature, that's a reference to 2013 paper. We also detected titanium-44 lines from SN987A, which is basically a point source for NuSTAR, so we cannot do mapping. And otherwise, these legacy NuSTAR observations, very long exposure time, give us very good statistics at other energy band, around 10 to 50 kV or something. So we detected a lot of non-thermal X-rays, and they gave us a very clean view of non-thermal X-ray emissions from these young supernovas. So these are the images I took from NuSTAR papers. So they're all about 10 or 15 kV. This is the non-thermal X-ray emissions. No contamination from thermal emission from X-ray band from these three remnants. And then I'm not going to go over details, but I would refer you to a very nice systematic study of young SNRs using NuSTAR and XM and Suzaku by Naomi Tsuji. She's our collaborator. She published a paper in UpJ back in 2021. She talked about how the Bohm factor changes over time by analyzing these SNRs. It's a very nice work. So I would suggest you can look up her paper. Okay, so let me talk about CASA, because that's our ongoing project. So back in 2012 and 13, NuSTAR spent 2.4 megaseconds. That's a lot for X-ray telescope. And then besides the titanium-44 Nature paper, the same author Brian published another NuSTAR paper called Locating the Most Energetic Electron to CASA. So that's sort of the point of NuSTAR. So if you look at the CASA's NuSTAR spectra on the left, so below 15 keV, you can see all these atomic lines, and then that's the thermal emission from SNR. But if you go to about 15 keV, you see nothing but a non-thermal emission. So 15 keV for CASA, that's like a dividing line. So on the right, that's the NuSTAR image of between 15 and 50 keV. I think it's the image decomposed. So you can see hard X-ray nodes on the western part, W2 and W4. And then there's some emission in the middle. So it didn't really follow the reverse shock. That's the inner circle, and the forward shock. And it didn't look anything like the radio or thermal X-ray emissions detected by Chandra. And then NuSTAR also did a nice spectroscopy study. And then they measured a very soft photon index around 3. So that was back in 2012 to 2014. Then meanwhile, Chandra was doing more observations to follow up CASA. So what they found out was based on the emergent epoch data, they detected proper motions and the variability of some of these X-ray filaments. So on the left, you can see Chandra 4 to 6 kV difference image between 2000 and 2014 data. And you can see some excess, some movements there. Details are in Sato's paper back in 2018. And he also published another paper in just this year by applying more sophisticated imaging analysis for medical physics. And then, but there's a caveat here. So the Chandra 4 to 6 kV continuum band, it's very narrow. And then I understand that their logic because it's trying to avoid atomic lines because there is no atomic lines between the mid-Z elements below 4 kV and then ion lines above 6 kV. But you still have a thermal continuum emission contaminating your 4 to 6 band. So really, you need to go to higher energy above 15 kV to have a clean view of non-thermal emission. So I also want to mention that if you go to higher energy, and then if your X-ray filaments or nodes have a higher B fields, their synchrotron X-ray spectrum should get softer and fainter more quickly, even with like a few year time scale. So on the right, we developed this toy model just to predict what happens to the synchrotron X-ray spectra after 5 or 10 years. And if you have a higher B field around 0.5 or 1 milligauss locally, the flux drops like rock, and then also gets softer. But if you have a lower beacon around 0.1 milligauss, and then spectrum doesn't really change, it just goes down just a bit. So NuSTAR comes in here. So we proposed a new NuSTAR observation with 200 kiloseconds. That's enough to characterize all these hard X-ray continuum emission. So it was approved, and the NuSTAR observed Cascade just last month. And our graduate student, Julian Wood, I think she's online today. She's running some analysis. So this is super preliminary, but I just showed the image. So on the left, that's the Cascade image between 15 and 50 keV flux map. So we corrected for this exposure map, vignetting effect, and background subtraction. This is what you saw back in 2013, 10 years ago. On the right, that's the brand new unit, which was taken last month. And then we tried to adjust the color scale just to do an up comparison. I would say something changed. For example, near the center, there's a CCO, center compact object, that's a neutron star. Just below that, I see some interesting blob here. And then this hard X-ray nodes in the western part, it looks kind of different. Even like slightly moved, but again, it's beyond the astrometric correction errors of NuSTAR. So this is what we have, just staring these images. But we will do more careful imaging analysis to find out what changed, what didn't change between 2013 and 2023. But based on, I don't see any dramatic change. Probably the B field is not that high, not like 1 milligauss. But probably something close to 0.1 milligauss. But please don't take what I said seriously. This is super preliminary. So let's go to Parson Nebula. So NuSTAR observed Crab, and then G2M5. That's another young PWN as a calibration sources. So we built up a lot of exposure time. So NuSTAR is a very good timing capability. So you can really take out the parser emission by a phase resolved analysis. So that's one good thing about NuSTAR. And then NuSTAR has a broad energy band. So you can do an energy results for morphology study or vice versa, which is a spatial result spectroscopy. So looking at the G21.5 image from NuSTAR, 3 to 6 kV all the way up to 20 to 25 kV, the size of the pyramid shrinks. So that's called a synchronous burn-off effect, because as the particle propagates from the pulsar, they cool down, and the cooling time is faster, shorter for the higher energy. So this is what you expect. So this has been beautifully measured by NuSTAR. Same thing happened to MSH 15-2052. This is published by Honjun. And then again, NuSTAR sees this so-called hand of God in 3 to 7 kV. And then it gets more and smaller as you go to higher energy. At the highest energy between 25 and 40 kV, you just see a compact nebula just around 25 to 40 kV. So that's how we saw in the initial stage of NuSTARs by looking at young PWN. So the next step is let's look at the little bit older PWN. So like I said in the beginning, we had a legacy program looking at DF495. That's another middle-aged PWN. So let's expand our program. So we observed 8 middle-aged PWN. So we published 3 papers so far in AppJ, and then Julian is writing another paper for Dragonfly, which you can see on the right. So what we found out was, NuSTAR detected hard X-ray, but it's from a very compact region around the pulsar. Unlike the soft X-rays, extending a much bigger regions detected by Chandra XMM. So that's one thing we saw. And then since NuSTAR's angular resolution is quite good for the hard X-ray telescope, you can really resolve the inner nebula in different energy band. So for example, this is a Dragonfly PWN, which could be associated with one of the lasso sources, 3 to 6 kV and 6 to 20 kV. You can kind of see the PWN size was shrinking. And then when we took the radio profiles of the Dragonfly PWN, you can see 3 to 6 kV profiles extended. And then if you go to 6 to 20 kV, it's getting smaller. So this is a quantitative way of measuring the PWN size. And then Julian did the Chandra XMM NuSTAR joint spectral fitting, and we have a beautiful power spectrum from 0.5 kV all the way up to 20 kV. So this is not the end of our analysis, but we did some SED studies. We used Yossi Gelfand's one-zone PWM time evolution model. So you can refer to his model. So it's a very nice model. He is basically injecting electrons from pulsars from T equals 0 all the way up to the current age, and then allocating this energy into magnetic field and the winds, and then calculates the pressure balance at its expand, and then tracks the pulsars, winds, radius, and magnetic field, which is essentially uniform to the one-zone model. And then it also tracks the electrons' energy distribution over time. So when you add them up, you can make a prediction for the current SED, which you can see. So after going through this exercise for Dragonfly, and then Eel Nebula, and the Boomerang PWM, which could be associated with one of the Russell sources, Pevatron candidates, what we found is overall B field is required to be low, something like a few microgauss. It's around the typical ISM B field, or even a bit lower. And then Emax for the electrons around 1 PeV. So it's consistent with Pevatron's picture. And then seems like all these middle-aged pulsar with nebula emitting a very energetic TeV gamma emission seems to be compressed by SNR reverse shock sometime recently. So there could be some kind of interaction between reverse shock and the PWM, maybe accelerating particles. So that could be some hint to the why the middle-aged pulsar nebula are emitting very high energy TeVs. So I also suggest, if you are interested in, I also suggest another approach of using multi-zone phenomenological model to apply to some of these NuSTAR PWM. So Hongjun's group published a paper, 2 papers, Park et al. 2022. So let me go to other galactic TeV sources. Just one slide on each. Okay, so W50 lobes. This is a very unique Pevatron powered by micro quasar inside. It's called SS433. It's a very famous black hole binary. And then it emits a bipolar radio jets going left and right, west and right, east. And then there's a game changer about this system after Hawke discovered the TeV emission from both the eastern lobe and the western lobe. So this is a discovery paper, Abe Sekar 2018, published in Nature. So this triggered a bunch of observations, follow-up observations, multi-wavelength span. So we have XMM, Chandra, and NuSTAR observation already approved and already happening. We finished the XMM NuSTAR observation. So we published the first paper on the eastern lobe here. And then NuSTAR detected a hard X-ray knot from the tip of this, the lobe, eastern lobe. That's the closest point to the SS433. And then we are working on another paper on the western lobe here. So Samar Safi-Harp and then her graduate student is leading this paper, and we should have Chandra observations done this year. So NuSTAR detected hard X-ray knots with a photon index around 1.6 in the both lobes. And then let's move on to TeV gamma ray binaries. So these are the rare binaries not powered by mass accretion. So people believe this is a system, binary system with a pulsar and the stellar wind colliding with each other and forming an intra-binary shock, IBS, and producing a high energy radiations. So NuSTAR observed all 8 known TeV binaries. That's why it's rare, so rare, only 8 binaries known. And then our collaboration has been focusing on HES-J0670. It's one of the 8 TeV binaries. And this binary system has 317-day orbital period. And then B companion star. B companion has the disk, as you can see on the cartoon here. So we observed this source first in the legacy program back in 2017 or something, working with a Veritas group. So far, we have done 4 NuSTAR and Veritas observation performed, and we published 3 papers in UpJ. And the most recent one is being Hongjun's group developed the IBS model, and they applied to the multi-wavelengths, SED, and the light curve data taken in the X-ray and TeV band. So So it explains many of the global features in the data very well, except one flaring phase here. So there's a very sharp spike appearing every 370 days. And then this is something we cannot really explain. So we suspect this flare is coming from some kind of B disk and the pulsar interaction, pulsar getting smashing into the disk, something happened. Maybe the electron density went up, B field amplification, or maybe photon density increased, right, for the inverse Compton scattering. So we have a Swift, NICE, and NuSTAR proposals approved, and then Veritas is joining us, and we're going to target the next flare happening in February 24. So stay tuned. That's going to be a very exciting multi-wavelength observation, targeting at this flare, possibly due to disk and pulsar interactions. Okay, so the next topic is the young star cluster. So lately, star clusters are becoming more recognized as one of the primary harmonic pematrons. One of the reasons is this discovery of gamma ray cocoons around the young star clusters, like Western 1, Cygnus region, and the Western 2. This is from a Young et al. 2019 paper. Then these star clusters have been emitting, producing energetic protons, and they're propagating throughout its neighborhood. So we looked into the, which young star cluster we can observe is NuSTAR. Western 1 has been observed by NuSTAR, but it was targeting a very bright magnetar, and a very bright magnetar was producing lots of background contamination. So it's not quite a useful data to study a diffuse X-ray emission from Western 1. So we proposed for observing Western 2 instead. And then there's a Hess source, J1023, associated with Western 2. So it was approved. And then we just had a NuSTAR observation last year. So again, Julian was analyzing this data. And this is the NuSTAR view. So on the left, I don't have an energy band here. It's a 3 to 10 keV. You can clearly see Western 2 here. It's more extended because it has a lot of stars, massive stars, maybe some binaries. And then on the right, you can see a pulsar, possibly with a compact pulsar with nebula. And if you go to about 10 keV, the Western 2 becomes much more compact. Possibly just it's coming from only one object, like colliding wind binary or something, and it's much fainter. And the pulsar with nebula is still there. But if you go about 20 keV, both of these sources disappear. We just don't see them. So I would say we have to do some joint spectral fitting with the Chandra XMM and NuSTAR, just to really understand the thermal emission below 10 keV and establish the presence of non-thermal emission above 10 keV in NuSTAR data. But just looking at the images, I mean, it just doesn't look like a strong non-thermal X-ray sources for something producing big gamma ray cocoon. Okay. So I'm going to go on to the galactic center. Starting from a radial view of the galactic center, this is a beautiful image taken by Meerkat. Sagittarius A star is here with a supermassive black hole. And you can see all kinds of radio filaments tracking a complex magnetic field structures. And then you can also see some supernova remnants emitting radios waves in this picture. If you go to the X-ray band, this is a 2 to 8 keV Chandra image of the central 2 degrees along the galactic plane and the 0.8 degrees in the vertical direction. So Chandra detected almost 10,000 X-ray point sources. Most of them are magnetic CDs, accreting binary systems. And they also detected some very interesting diffuse X-ray emission. So if you look at this image, you see more concentration of X-ray sources, both in the point sources and diffuse emission near the center. That's because you have more objects and gas around the supermassive black hole, and also because Chandra and many X-ray telescopes spend more time looking at the galactic center, staring at the Sagittarius A star with a longer exposure time. So you go down to a fainter end of these X-ray emissions. Okay, so yeah, let's go up to like a TeV gamma ray band. So this is Hess image of the galactic center. Again, it's a similar setup for 2 or 3 degrees. It's actually bigger than 2 by 0.8 degrees. So Hess detected, Hess and Veritas Magic detected 2 bright point-like sources. The brightest one is Hess J1745, that's in the middle. And then another one is a G0.9 plus 0.1, that's a young SNR pyramid system. And if you remove these point sources, then TeV images actually reveal more diffuse X-ray emissions. I'm sorry, diffuse TeV emissions. They are associated with a molecular clouds. So Sagittarius A has some clouds, and then Sagittarius B is the most massive cloud in the center. Sag C is on the other side, and Sag D is another cloud. So there's a correlation between diffuse TeV emission and the molecular clouds. That's been well known. So let's look at the hardware X-ray band. Okay, so on the left, that's the integral 20 to 40 kb image of the galactic center. Integral is not a focusing telescope, so its angular resolution is around 12 arc minutes. And a NuSTAR has a much better angular resolution, less than 1 arc minute. So there's a blobby hard X-ray emission between Sagittarius A star and 1 in 1743. That's a bright X-ray binary. And then NuSTAR resolved this hard X-ray blob into discrete substructures here. So what do you see here? So we see some point sources. Number one, these are likely to be an X-ray binaries and magnetic series. And around the Sagittarius B star here, you see an elliptical diffuse hard X-ray emission in the central 10 parsecs, which I will talk about. And then this diffuse emission is coming from a molecular clouds in Sag A complex. And then you see something else, like X-ray filaments. These are the unique X-ray filaments only found in the galactic center, which I will talk about too. So let me start with the X-ray filaments. So Chandra, with a better angular resolution, down to 1 arc second, the resolution. So they detected 25 filaments in the galactic center so far. So they are usually located just around the center, I would say within 20 or 30 parsecs. But if you go outside, you don't really see X-ray filaments. On the other hand, if you go to the radio band, Meerkat detected almost 100 radio filaments. You saw the picture before. That's what I'm talking about. You see a large arc here, you see all kinds of filaments. But in the X-ray band, it's around 25, okay? And then these X-ray filaments have a very diverse class of, how they look like, and then things like this. So a few of them are likely PWN because Chandra detected point sources, which could be a pulsars. And then, yeah, these are the non-thermal X-ray filaments. So they're emitting a synchrotron radiation through the high B field, and then they should have some kind of highly energetic electrons in TeV or PeV band. So NuSTAR detected 4 of these 25 X-ray filaments above 10 kV before. So that means these 4 hard X-ray filaments have a higher magnetic field and or higher energy electrons. So let me start with this one. So G0.13 is likely to be a PWN. So you can see a Chandra map here. So you see a filament, but there's a point source, clear point source here with a non-thermal X-ray emission. We don't have any pulsation detected yet. So officially it's not a pulsar yet, but just based on morphology, this looks like a PWN. So NuSTAR detected this filament above 10 keV, and then Hess catalog of the Galactic Center actually listed a new TeV source for Hess J1746. So this Hess source and this filament slash PWN, they are associated with each other. Okay, and then let's talk about the second brightest TeV source in the Galactic Center. So this is a Veritas image of the Galactic Center. Again, you see a very bright spot in the center, J1745. And then this is the second brightest one I'm talking about. So that's a very young SNR PWM. And then NuSTAR detected this source. It's hard to see here. NuSTAR detected this source up to 30 keV with a beautiful non-thermal spectrum from 3 to 30 keV. So we measure the power index around 2.3. And then right now we are working on one zone pulse of wind nebula SED modeling. You're working with Yossi Gelfand's group. So let me talk about some non-PWM filament. So this is the brightest X-ray filament, about 9 parsecs away from Sagittarius A star. So this filament was detected in the X-ray band. This is the Chandra image. I don't see any point source. But if you look at the radio band, it looks like a bundle of magnetic field tubes. So it just doesn't look like a PWM. So it's some kind of magnetic structures with very high energy electrons coming in and emitting synchrotron radiation. So NuSTAR detected this filament for Sagittarius AE naught up to 50 keV. And then photon index we measured was about 2.3. So what's the scenario of having some electrons at this location? So how do you get the TeV electrons in situ, right, when there's no PWM pulse around, or not even SNR? So one scenario we came up with is illustrating this cartoon. So you have some kind of particle acceleration, accelerator around Sagittarius A star or SNR or something, okay, star clusters. So they emit the PeV or TeV protons. They don't cool down that fast, not as fast as the electrons. So they keep going. They collide into a molecular cloud close to the filaments, and they produce secondary TeV or maybe even PeV electrons. And then these electrons enter into the filaments. And then if you have TeV electrons, they emit X-rays. If you have GeV electrons, it's easy to produce. You're going to have a radio filament emission. That's what we see. So this is like a 2 steps. Okay, you have protons hitting molecular clouds and then producing secondary electrons. They're going into the filament. So that's one scenario. But like I said, we have 25 X-ray filaments. They probably have a different stories, depending on the locations and then what's nearby their filaments. Okay, so let me talk about molecular clouds next. So if you remember, diffuse TeV emission, this is correlated with a molecular cloud, so it's worth looking at molecular clouds. So only in the galactic center, these cold molecular clouds are emitting X-rays in 2 different ways. So this is, so they are emitting X-rays through the neutral ion K alpha line at 6.4 keV. And also they also emit the non-thermal X-ray continuum. So this is the 6.4 keV neutral ion K alpha line map back in 2000 and 2001, and then 11 years later. So you can see Sagittarius A molecular clouds, they're not really dimming. But if you're talking about individual clouds, we have different stories. Some of the clouds are brightening over the last 10 years. Some of them are actually dimming. So something's going on there. But if you look at Sagittarius B, it has been dimming over the last 10 or 20 years. Same story for Sagittarius C. So you don't really see emission back in 2011, 2012 compared to 20 years ago. So we have 2 X-ray components. The first one is that you might have some reflection of X-ray outbursts from Sagittarius A star. Some people believe Sagittarius A star had a gigantic X-ray outburst, maybe lasting for 10 years or something, going up to 10 to the 39, 10 to the 40 ergs per second. And these outbursts are going out and then illuminating these clouds. And with some time delay, we see them now. So that's a time variable component. At the same time, you also should have some steady X-ray emission, because there are lots of cosmic rays, like I said, they're hitting these clouds, producing X-rays, ionizing ion line, and then you see a 6.4 keV neutral ion line. So that's more relevant to a TeV emission. So we really need to see these 2 components separately. Okay, so looking at the Sagittarius B2, that's the most massive galactic center cloud. So like I said, ion K alpha line has been decreasing over the last 20 years. And then that's the nice spectrum. You see an ion line here. Otherwise, you see a beautiful X-ray continuum. This is a NuSTAR image of the ion line and then how it's a continuum. It's very concentrated near the core of the Sagittarius B2. It's a very large structure, but near the core, you have very high Coulomb density. So you might have a better chance of trapping photons or getting more collisions through the cosmic rays. So at some point, flux keeps decreasing, and then this variable component, possibly due to gigantic X-ray outbursts from such as A star being reflected, should hit the floor, and then we should see nothing but the cosmic ray component. Then maybe it's time to compare with the TeV data. So let me wrap up my talk by looking at the very center. So this is a central 10 parsec region in 20 to 40 keV. So what do you see here? You see this elliptical hard X-ray emission. We call it the central hard X-ray emission. We nicknamed it CHXE. We published a paper in Nature back in 2015. And then you see this bright X-ray filament I talked about. And there's also a molecular cloud called the MC1. So MC1 cloud has variable X-rays, starting from being bright, and then it was getting dimmer. Okay, so what's this CHXE? Is this something like diffuse gas, plasma, or some kind of point sources? So we believe it's unresolved population magnetic series. Why? Because if you look at the distribution of this CHXE, it exactly matches the nuclear star cluster with a bunch of IR sources or stars or binaries. And then we also analyzed the XMM and then Chandra data, the low energy from the same region, jointly feeding with a NuSTAR, and then it's very nicely producing a thermal plasma emission with 35 keV with atomic lines. So it's not a non-thermal emission. It's basically a hard X-ray tail of a thermal emission when the temperature is 35 keV. So this is also backed by Chandra analysis, looking at the bunch of point sources in the same region and building up the luminosity function, and then mostly explains the CHXE luminosity. So we believe this is a magnetic seed. So that means it's not related to the TeV emission in the galactic center. Okay, so let's look at the very center a few parsecs, 20 to 40 keV. So we have multiple NuSTAR observations, different pointings, but we did a very careful job of applying astrometric correction by registering Sagittarius A star flare. There's another point source called Cannonball, that's a runaway neutron star. So we combine all the images. This is what we see in 20 to 40 keV. So there's a Sagittarius A star, but there's another X-ray filament, which is likely the PWN. So this is a Chandra image of this X-ray filament. You see a point source and then extended tail. So this is again likely to be a PWN based on the morphology. So the 2040 keV emission is centered on this PWN, not the Sagittarius A star, not the star cluster IRS certainly. And NuSTAR can resolve this. Let's go to the higher energy, but same region. So I see two sources. One is again this PWN, not the Sagittarius A star, and then mysteriously there's some kind of outflow looking or some kind of protrusion looking hard X-ray emission only detected about 40 keV. So the green contours are the circumnuclear disk, which has a very high density. Maybe it's absorbing a lot of soft X-rays, so we don't really see a soft X-ray counterparts. Maybe it appears only about 40 keV, but still it's kind of mysterious. I don't think it's a transient. I don't think it's some kind of known structure. So we are puzzled, still puzzled. Okay, so finally, the PWN right next to Sagittarius A star, we believe this is actually a counterpart of the bright Hess source, the TeV source in the center, just because it's the most prominent hard X-ray source in the center parsec. If you have a particle accelerator, some kind of high energy particles, it should be very bright and hard X-rays. So that's what we see. So when we apply the one zone PWN model for this system, there's no radio emission. Where there's no radio detection, we use the NuSTAR data here. We use the Hess data here. And then this is what we found out. So it fits the broken power electron distribution. And then E minimum is around 0.5 TeV and E max is around 200 TeV. So and then the age in the system is around 10 to 4 years. And this is consistent with Hinto and Aharonyan 2007 paper. Okay, last topic. I'm running out of time, I guess. Okay, so let's talk about X-ray astrophysics in 10 years, in the early 2030s. So as you know, Chandra and XML has been running for like 20 years. To be honest, they're aging. And then NuSTAR has been running for 11 years, Swift even more. So it's time to think about the new X-ray probe in the future. So as you know, Europeans are proposing for Athena project, but their launch date is pushed until late 2030s, and they need to design the telescope, things like this. So we don't know what's going on. But in the US, NASA had this Decatur survey, and they're requesting, we should have some X-ray probe mission with a total budget around $1 billion. It's about the same as Chandra's budget. So there are 5 candidates right now, including HEXP, which is what I'm involved as a co-I, and then Galactic Science Lead. So we have StrobeX. This is basically a super timing, X-ray timing machine telescope. Super nicer, XT type, telescope. You also have a LEM and Arcus. They are looking at the very soft energy band, even below 2 keV, looking at the lines, atomic lines. And Axis is a super Chandra, so they're going to be having a very good angular resolution, and then operating 0.2 to 10 keV. So only the HEXP has a very broad energy band, just like NuSTAR. So which mission will do well to study the non-thermal emission and then particle accelerations, based on what I said. So more about HEXP. So its nickname is Next Generation All-Purpose X-ray Telescope. So you can just call it, Super XMM NuSTAR Telescope, whose energy band starts from 0.1 to 80 keV. For the higher energy band, we are still debating. We are still trying to study. So we became more conservative to go up to 80 keV. But if it's selected for the phase A study, we're going to study for the coating of the mirror and everything. And then the energy band might go up higher, at 100 keV, even higher. So otherwise, we have one low energy telescope from 0.1 to 20 keV with a 40 arc-second angular resolution. And you have 10 NuSTAR type high energy telescope going up to 80 keV. And the angular resolution is so much better than NuSTAR. Remember, NuSTAR's resolution is around 58 arc-seconds. It's going to be 3 or 4 times better. So this is a simulation of CASA for HEXP in the middle. Just for comparison, you can see NuSTAR and the Chandra image. So you can really see all these substructures and HEXP simulation, something closer to Chandra, what Chandra saw. And then compare the NuSTAR's broad image. So again, HEXP will be uniquely suited for studying non-thermal X-ray sources, and then eventually understanding extreme particle accelerators in our galaxy or beyond our galaxy in synergy with CTA and other TV telescopes. So this is my summary page. I'd like to thank my collaborators from NuSTAR, Veritas Folk, and many other instrumental teams. And then again, NuSTAR detected non-thermal emission from many X-ray sources, including galactic TV sources. And then we measured photon indices from many of these objects, from very hard ones like Jupiter magnetars down to very soft photon index like CAS-A. So it's up to you if you're doing some modeling theory, take our photon indices and then just wonder why, what's causing these different photon indices. And then we also detected photon index indices from different regions, and then potentially different times, like CAS-A. I'd like to re-emphasize the multi-wavelength CD and morphology studies are very important for all these galactic TV sources. And then in 10 years, we hope to have a nice X-ray probe mission, hopefully HEXP working with COSY, CTA, IceCube, Gen 2, Larsen Hawk, many other telescopes. And then this is kind of my view. So everything, all these particle acceleration, you have interplay of a particle acceleration, propagation, and cooling. And then we should probably see this as like a 4-dimensional program. You have morphology X and Y, time evolution T, and photon energy. So photons are moving around, between in this phase space. So we really do need a broadband and a high sensitive, X-ray telescope in the 2030s. I believe that's HEXP. and working with other telescopes. So if you have any questions, and if you have some collaboration ideas, please contact me at this email. Thank you for listening, and I'll stop here and take questions.
Great. Thanks a lot, Kaya, for a great talk. Okay, so this is the time for discussion, I guess. Any questions? Okay. I heard X-rays, so. Okay, Evgeny raised his hand, so go ahead, Evgeny.
Evgeny?
Yes, thank you for your talk. Was very clear. Just two questions. One is about the light curve of gamma ray binary. Could you go to the slide?
Yes, I'm getting there. Yes.
Not yet. Yes, this one. Okay, there are two curves. I probably missed your explanation, or you didn't say about this. There are two curves, which are the blue and the red dashed curves. What are these slow and fast curves? What they describe?
Yeah, good. I mean, that's a very technical question. I mean, Honju, you're online. Would you like to answer this question instead of me? You assume the slow and fast electron flows in the IBS, right? To fit the data.
Yeah, right. So basically the light curve is very complex. So we to match the data, we have to assume two different populations in the intrabinary shock. So one is slow, which shows orbital modulation because of the changing distance between the pulsar and the companion. That is red. And the other is the blue curve, which is the Doppler beaming effect, where the maximum occurs at the inferior conjunction of the pulsar, where the pulsar is behind the companion with respect to us.
And what's the reason why the two curves behave in some sense they behave in counter phase? One has a minimum, another one has a maximum. Is it just an assumption, or there is a reason for that?
Well, that's basically, if we know the orbit, so if we have a nice orbital solution, we basically know where the periastron is and where the inferior conjunction is. But for this particular source, the orbit is not well known, so we adjusted the orbital phases to match the light curves. So the red curve has a maximum at periastron. The blue curve has a maximum at the inferior conjunction.
But yes, I see. But the question is why? Why they behave so
we basically
different?
adjusted the orbital parameters to match the data.
Oh, so it's kind of assumption. You don't have an answer why it should be like this. It's just the result of fitting to observations. Is it correct?
Well, basically at the periastron, this separation between the pulsar and companion is very close. So the magnetic field in the intrabinary shock is stronger. So that's why the red curve has a peak at periastron, which is assumed. And at the inferior conjunction, the Doppler beaming is strong because we are looking at the shock tangent. So that's why the blue curve has a maximum at 0.75, which is the assumed orbital phase for the inferior conjunction.
Mm-hmm.
So we basically assume that the orbit has a periastron at 0.25 phase and the inferior conjunction at 0.75 phase. That's what we assume. Once we assume that, then the maximum occurs at those phases.
Okay. And then a second question is about the X-ray filaments. Could you give just a few numbers? What's the typical size of these filaments, and what's the expected lifetime of electrons? I mean the X-ray emitting electrons.
Yeah, so the typical size of these filaments, it depends, right? So let's look at this Chandra image. So some of them are long or not, right? So typically, because Chandra resolved these filaments, but not the other one. So they're about 5 to 20 arc seconds. And then in terms of parsecs, 25 arcsecond is 25 arcsecond is 1 parsec. So I would say something like 0.3 to 1 parsec in size. And then you're asking me about the lifetime of the electrons. I mean, depends on the B field. And then I don't know how they measured, maybe estimate the B field, but they say B field around in the filament should be around 0.1 to 1 milligauss. If you take a higher number, 1 milligauss, and then and if you have if you see a hard X-rays, I think the lifetime of these electrons could be as short as some years, right? So we might see some variability possibly.
So it's marginal. I mean, if you want to supply the electrons from the sides, then it's kind of marginal solution because they are almost cooling in flight.
Yeah. That's right. So if you believe what we say, so you have to take some electrons from nearby, like in the molecular or something. They have to be close by, and then they cannot cool down fast. So it has to have some low B field on the way before they enter the X-ray filament, and they make hard X-ray. So I think we should really look at where the molecular clouds are and where the X-ray filaments are located. Some of the radio filaments show X-rays, but not all of them. So I think we should look at all of them systematically, and then also, just looking at the filaments, right? Why some of them are short, why others are longer, right, brighter. And then what about the power index, right? Maybe you see a harder photon index for the X-ray filaments near the center. Maybe they get softer and then fainter. So I think we should look at them all together to answer your question more systematically.
Yeah, I see. Thank you.
Just to follow up, Evgeny, do you see a range of spectral indices like in this picture you show right now on your screen? Do they have different spectral indices? Yeah,
that's a good question. It's hard to see. Okay, so number one, even within the filament, you see a spectral variation. Okay, I remember, that this guy G0.13, the point source, which is probably a pulsar, has the hardest spectrum. As you go away, it gets softer, just like a PWM. But other, filaments, you just don't have enough counts from the Chandra. And then NuSTAR detected some of them, but I would say for most of the 25 X-ray filaments, you just don't have enough statistics measure the power, photon index well. So I would say, it's more like 1.5 plus minus 0.5 versus 2.0 plus minus 0.8. That's a kind of measurements we have. So we cannot do some kind of spectral imaging, distribution mapping yet. You need head speed.
Okay, thanks. All right, so Yuri. Yep, go ahead, Yuri. Yeah.
Kaya, thanks very much. It was a great talk. I had a couple of questions. So the first one is, what do you think is the origin of this hard X-ray nodes, both in CASE and in SS433? Do you have any ideas?
You mean this? You mean how it's not in CASE?
That's right. This is CASE.
What's the origin? Yes. Okay. So this.
And you had similar ones in SS, well, kind of similarly mysterious ones in SS433. It wasn't associated with any of the other structures.
Yeah. Okay. So for CASE, so based on the Chandra observation, so do you see all these arrows going inward?
Yeah.
Okay. So what they found out was, so around the W2 and W4 hard X-ray nodes, these X-ray filaments resolved by Chandra, they look like they're moving inward. So what they're saying, so you see a reverse shock here, and then at the age of CASE, at the young age of CASE, you can have a reverse shock, but it should be still moving out in our, in our observer's frame, but it's actually moving inward. So what they're saying is basically you have some kind of dense cloud here. Sato's paper has a very nice cartoon. And then you have a reverse shock happening earlier and then coming back. And then it's hitting these some kind of high dense blob and then producing these X-rays. So what I'm saying is this is the region you have reverse shock hitting something hot, something dense, and potentially magnetic field amplifications. But that's all I know. And I'm also puzzled by this very soft photo index of around 3. I don't know why, and I'm not sure if anyone's talking about this.
Kaya, why you are puzzled? The very soft X-ray spectrum implies the region of cutoff region, so that is normal. Actually, in most cases, we see in synchrotron sources steep X-ray spectra. It means just you cannot measure entire spectrum.
Yeah, Felix, this my impression is just looking at many other objects, non-thermal sources. I'm seeing a gamma of 1.5 to 2, and then seeing a gamma of 3 or maybe even 3.5 in some of the knots in the cassette. It just looks surprising. But if it's totally normal near the cutoff, maybe that's fine. But I don't think, I'm not sure if other SNRs have similarly soft photo indices like cassette.
Okay, thanks, Kai. And my other question was about the Dragonfly.
Yeah.
You mentioned that you were using one zone model by Yossi Helfand, but then at the end, you, in your conclusions or in your discussions, you said that there is a need to develop multi-zone time-dependent models. Did I read this correct? And the question is, do you actually require multi-zone time-dependent model to model something like Dragonfly, or is one zone completely adequate and there is no data to use to make use of the multi-zone model?
Great question. Okay, so this is not my word, but whenever I talk to Yossi, he visits here in New York every summer. So yeah, he's the one who developed the one-zone PWM, and he knows its limitation. And then he's the one who said we need multi-zone PWM, but it's a big step to do the modeling. And why? Because if you look at the PWM in multi-wavelengths bands, right? Usually X-ray emission is very compact, and if you look at the radio and TV, they're much more broader. So where do you fit, right? I mean, do you assume? I mean, these electrons actually produce in different times and propagate, right? And then you see, X-rays and TV and radio, giving you different sizes. So, but you have to just assume everything is in one container, things like this. So, and plus, we have a very complex morphology, right? I was showing G21.5, which is simple, but if you have something like the hand of God, right, what do you do? So, I think just because you have a different morphologies and different sizes in different energy bands, I think we need like a multi-zone approach in the end. I mean, for now, just for convenience, we just have to assume, take a large region, collect all the X-rays, collect all the TVs, collect all these, radio band, and then just combine them into one zone. But again, we are basically ignoring the propagation effect, right? We are ignoring the size measured in different energy bands. So we can do more with multi-zone model if we have one.
Okay, thank you.
Yep. A follow-up question to that maybe is, like when you do time variability, some people make SEDs with data points that are averaged over years, and then they compare it to data points averaged over like seconds or minutes if it's from the optical observations, and that doesn't quite make sense. So similarly here, there have been discussions between like Lhasa and TV Cherenkov instruments disagreeing, and its angular resolution size. So what like the plot you made there, what kind of radius are you averaging over, or is every region, spectral region, different averaging radius, in which case it doesn't quite make sense, as you were saying we need a multi-zone.
Oh, wait. For the drug, say Dragonfly.
Yeah, say Dragonfly, yeah.
Okay, Julian, do you want to take this? You did analysis and modeling.
Sorry, could you repeat the question?
Yeah, no, so just as Kaya was saying, and it happens in the for time variable sources, people plot STDs with the data points integrated over different time intervals. And here, what spatial integration do you use? Are the points consistent with the same sort of extraction radius, or so to go discuss further what Kai was saying about the need for a multi-zone model.
Yes,
For extraction radius.
right, that's correct. The extraction radius is the same as the observed sizes.
Okay,
Observed sizes.
and if you mate them the same, I guess, all right, then I guess it doesn't matter if you've resolved the source, but for like Casset, there was a lot of the X-ray knots have steep emission, but there was green emission in the middle. Is that does that have a hard spectrum? And then when you blend everything together, does that cause issues? Like, is Casset actually a hard source if you ignore the X-ray hard X-ray spots?
Yeah, that's a good question. Okay, so I think if I remember the Brian's paper, he segmented all these different regions, right? He measured like the photon indices from different regions, and I do remember there are mostly like around 3 photon index of 3, and maybe there are some variations. Okay, but there's something very puzzling here. Okay, so integral telescope looked at observed Casset for a long time. Okay, million seconds something, and then they're like going for a higher energy. Okay, they cannot resolve Casset like NuSTAR did. They found a harder photon index, like 2. And how to reconcile between the entire remnant, higher energy giving you harder photon indices versus NuSTAR's resolving all these hardware knots, giving you a photon index of 3. I don't know. Maybe the answer is there could be some kind of underlying non-thermal Bremsstrahlung emission, which might have like a harder indexes. So like Felix said, it's a very steep spectrum. If the B field is higher, eventually these plasma will cool down, right? And you're gonna hit the floor of some kind of non-thermal Brems emission, some kind of baseline non-thermal emission. I don't know, maybe integral with all time average. So we might see something underneath. But I don't know. It's we just have to see Cassettes over time.
Yeah. And would you lose such a component when you do like background subtraction for NuSTAR? Because you might take an annulus that's contaminated by a non-thermal Bremsstrahlung and just remove it. Is that an issue for when you?
Yeah, so Casset is actually not covering the entire field of view of NuSTAR. So you can actually go off the Casset and take a source-free regions for the background modeling, and then extraction modeling. That's what we're doing there. So we subtracted all the regular background subtracted. So what's left here, what you're seeing here, is nothing but Casset emitting something.
All right, that's pretty cool. All right, are there any other questions or? If not, I had a couple other questions, but let's see if anybody else wants to ask. So I was wondering, for the galactic center, you said there was a thermal component with a temperature of 35 kV. Oh, okay, Felix has got a, well, let's see. Let me finish my question, then Felix can go next. Yeah. Where was that? Yeah.
Yep, here, yep.
Is that seemed pretty surprising? A high temperature, it's not so typical. It should cool pretty fast. I mean,
Paul, that's a good question. If if people are not familiar with magnetic CD, so look at this picture. So you have a companion star, reaching filling up the Roche lobe, right? So then you start having some mass accretion. Okay, it's gonna form an accretion disk. But because of the magnetic field is high from the white dwarf, it's gonna be a truncated accretion disk. For the case of intermediate polars, if the magnetic field is around 0.1 to 10 megagauss or something, so that's very low. Then you're gonna start having this magnetic it's like accretion flow channeled along the magnetic field, going straight to the pole. Okay, then you have a basically free fall plasma going down. At some point, it's gonna reach the sound speed, and it's gonna produce a standoff shock, and that's gonna really heat up the gas up to 60 kV or 50 kV. And that's actually related to mass and radius of white dwarf. And then once you have a shock, heated gas, it keeps going down along the gravity, right? With the gravity and along the magnetic field, it's gonna radiate cooling. That's basically a cooling flow problem. Okay. then it's gonna hit the white dwarf. So we actually have a model, it's called MCV spectrum model this. So you have some kind of accretion column, cooling flow program starting from a 60 kV at the standoff shock going down. If you take the average temperature, it's easy to get 35 kV if you're talking about intermediate porous. That's well known from all these local IPs. So this is a special case. Okay, I talked about lower plasma temperature, black white temperature, 0.1 or 1 kV, neutron star, X-ray binaries. But when it comes to these special magnetic CVs, they can reach out to 35 or even higher temperatures. So they're the sort of like a background for the hard X-ray emissions against the diffuse gas, diffuse plasma, but it's there because there are lots of CVs in the center.
Okay, I didn't know that. Okay, that's
Felix?
Do you hear me, Paolo?
yeah, I can hear you.
Oh.
Yeah.
Oh, finally. Well, I have a very bad internet. I tried several times. Kaya, could you show again this CD of Dragonfly is 14 page, I guess.
Yep.
Oh.
Is
Felix,
1.4.
Can you repeat again, Felix? I think.
Yes, this one. My actually is disconnected the slides with the voice, so somehow my internet is really very funny, operating strange way. The question is the following: what is the spectrum of X-rays? You show only the flux. Here, it's common thing just to show the flux when for a CD, in particular for possibly nebulae, and that could be misleading often, because imagine your flux spectrum is like E-2, hard but not very hard. That this model could be excluded in that case. So I just want to say you should not only try to match the absolute flux, but also to explain the spectral index. And often, not only here, we can see this kind of ACDs when showing only the absolute X-ray fluxes.
Sorry, Felix, you're kind of bringing up, if I understand what you're saying, are you saying, let's say, if you take any X-ray PWM, there's a spectral index variation from the center to the outside, like a spectral softening. And then are you saying we cannot just take some...
No, what is... Just simple question, what is the spectral index, photon index of this yellowish zone?
Well, what's the spectral index of this multi-zone model?
No, I don't know.
Sorry, one zone model.
Okay, one zone, whatever it is. Yes, what is the spectral index here?
Yeah, so it's actually a superposition of different components. So for example, if you look at the lower left side, so Yossi's model is actually producing electron distributions over time, throughout the lifetime of PWM. So you can see this. And I believe what he did is he actually basically integrated everything to produce this. So you don't have a single model.
I'm not talking about model. I'm talking about measurements. What is the photon index for X-rays?
Okay, Julian, what's the photon index of this measurement?
Photon index of X-ray?
Yeah.
Is it consistent with the model? Yeah, is what he's saying. Yeah.
Yes. It's about 1.8.
So it's agrees with more or less with the theoretical. Yes, because it should be shown. I mean, very often we're trying to get the absolute fluxes, but then spectral index could be much different. So it's important to show spectral index. This kind of just zone is not sufficient to conclude whether you could explain or not, especially in this specific case, there are few very, the magnetic field is very small, and then is assumed extremely large energy for electrons, 1 PeV. It is almost unrealistic. So how to get 1 PeV maximum energy of electrons? Nevertheless, we can assume, but in that case, we should pay attention to the spectrum in different parts. So, okay, you said it's a 1.8, so it's more or less agrees with the slope of the theoretical curve.
Yep.
Okay.
As you can see on the residuals on the bottom. So before our papers, we didn't see any SED modeling of these Peterman papers, showing any residuals. So they just plot and eyeball, like, some kind of, matching between the model and then the data. But we had some comments from one of the referees, and we should be showing residuals. So that since then we are showing residuals just to show how good the fit is. And I would say this is a good fit.
Well, at least, I mean, just from only from this figure, I would say it is a good fit. It's because it's missing, because NuSTAR gives energy spectrum, so should be shown energy spectrum. I mean, not the zone of the absolute flux. In specific case of NuSTAR. So I like to say, so just exactly only from this spectrum, you could say you have a good fit. You just match absolute flux, which is easily done by assuming magnetic field. Magnetic field determines the amplitudes of X-rays. But in order to really show that it models gives that, anyway, you see your model gives you 1.8. If measurement is not 1.8, but let's say 2, then I would say there's no agreement.
Yep.
So that is my point. I mean, this is just only the flux is not sufficient. By the way, this was my also a second question. Very often for synchrotron sources, you give not the spectrum, but this what is called S-cut or whatever this Reynolds feat of synchrotron emission.
SR-cut.
Yeah, that is a bit. In many papers we could see these parameters instead of showing on the plot the real spectrum. What is the reason? Why don't show spectra? But in a quite large number of papers, you simply give these parameters for this E0 and whatever alpha for this model, but you don't show spectrum.
Yeah, Felix, I agree with you. I was looking into Tycho NuSTAR paper and maybe Kepler paper. They jumped onto SR-cut model. I want to see the simple parallel fit and then give me a photon indices, right, at different locations, but they didn't use it. And they just show like SR-cut models, this E-roll, and then some, Jansky type, normalization, things like this.
No, normalization is fine, but this model is very, how to say, it's very nice, a great experiment with a good spectral capability. And instead of showing experimental spectrum, you just give parameters for the fit.
Yeah, I agree. Yes.
Which,
I'd rather see like a phenomenological model fitting like a parallel for the first step. Yes. For everything.
Yes, parallel is more or less is fine, but when that feed actually, well, I could be here even more critical. It's a wrong background. It has absolutely wrong background, because it's based on we criticize that in a couple of our papers, because it's based on the assumption you calculate synchrotron emission, assuming delta functional approximation. And very often spectra you measure are in the cutoff region. In that case, delta functional approximation gives absolutely wrong parameters. Just simple example, Hardy spectrum, the SOFI spectrum in the cutoff region for monoenergetic electrons is exponent, right? Pure simply exponent, E minus E over E0. And then this delta functional approximation gives you the beta in the electron exponent half. So formally, if you have a large beta, you could get more than one, so you could get steeper spectrum than monoenergetic electrons give. Synchrotron spectrum cannot give softer spectrum, sharper exponent cutoff than monoenergetic electrons. So this is completely wrong assumption. It works in power law part, but certainly does work in cutoff region. And very often when you are detecting X-rays, that was my comment was, if you see steep spectrum implies very often not power law steep, but a region when we are in the cutoff region, in the cutoff part. So that is, for example, for all of blazars, we see very steep X-ray spectra, and we are not surprised. The reason is just this is the cutoff region. So, but if you are in cutoff region, then this delta functional approximation is wrong, and that is this what is called S-cut, whatever, is based on that assumption. So that is very dangerous, extremely dangerous, wrong theoretical model, and practically you do not give the experimental data. In experimental papers, NuSTAR papers, instead of giving a spectra, you give some kind of hypothetical fit. I mean, the S-cut. So that was because it's really the NuSTAR is much better than many other X-ray detectors because of the broadband part. And also, if you are talking about synchrotron, very often, if you go hard X-rays, we appear in the steep, we appear in the cutoff, exponential cutoff region, not simple exponential, so that's cutoff region. And in that case, to fit this with a theoretical model which has a wrong background assumption, that is a bit not the best approach. Let's put it this way. Okay.
Felix, just one comment. Yeah, can you recommend some papers on this topic you just mentioned, like talked about? I mean, do you?
Okay, we just criticize in our the paper, for example, we have in GEO9 paper based on that. And then I can, if I don't like to take time of people here, but I can explain you how Reynolds interprets that. He says, so he makes two assumptions, two, let's say, not correct assumptions. One, the electron spectrum has exponential cutoff. Typically, electron spectrum could have exponential cutoff, but basically it is steeper. For example, shock acceleration gives you exponent square. And then the spectral index in a synchrotron relates to the spectral index in the exponent for electrons in a way like beta over 2 plus beta. So if beta is 1, simple exponential cutoff in electrons, then spectrum in a synchrotron will be 2 over 2 plus 1, but not beta over 2, which is a delta functional approximation. Now, making two wrong assumptions, one in electron spectrum, assuming beta 1, but it should be beta 2. And then second wrong assumption, that delta functional, which will be beta over 2, result gives right result. So two mistakes give you correct result. But it is accidental. It is only one case. In general, if you consider the problem, that could be ring. In fact, I mean, if I say if electron spectrum is steeper than beta more than 2, then it comes nonsense delta functional approximation, because you get steeper spectrum in a synchrotron than gives monoenergetic electrons. Any rate, so it was written, but my point was not to, we mentioned that few times even to Reynolds, but every time he says numerical, it is a good approximation. I mean, it's terrible approximation, delta function approximation, if you are in the exponential cutoff. I did say that. I mean, who cares? We do many mistakes, but in that case, you just don't show experimental results and give a fit based on this assumption. So that was just a side remark. Sorry.
Yeah, I hear you. Yeah.
Right. I think we need to, myself have to go. Also, just one last, in that plot there, there's no actual NuSTAR data though. Is that true?
Yeah, that's right. I mean, Julie, you didn't include NuSTAR data because that's coming from a compact nebula, and it's about like 10% of a NuSTAR, 10% of an XMM flux. Is that right? And then because it's not a multi-zone model, so you just have to take the larger region, right, coinciding with the TeV or radio size. Is that right?
Right. Also, NuSTAR observation couldn't cover the entire region because the field of view is smaller. So I couldn't extract the spectrum from the entire outer nebula.
Okay.
Yeah, but my comment was not for this. It was for typically it comes from supernova remnant NuSTAR papers, if I understand. I mean, not for to all NuSTAR, but
yes, I guess Felix's point is plot the actual data and then
yeah,
make it independent of the model. All right, I think many of us probably have to go, so we're gonna thank Kaya once again for a great talk and telling us about hard X-rays. And I just want to remind everybody before we go that there will be a talk again in 2 weeks, and we'll go back to particle acceleration theory, where we'll hear about PIC simulations of turbulence and reconnection by Luca Comiso. So come back in 2 weeks. And thanks again, Kaya, and we're gonna say goodbye for today. All right.
Okay, thank you.
okay, thanks.
Have a good day.
Bye.
Bye. All right.